but these do pose a risk to Earth, these near-Earth asteroids. And we're going to be talking about the risks a little bit later on. But actually, I did just want to do one little thing tonight because we've had so many new members today. And I just wanted to take this opportunity. In fact, I've got even more just coming up now. I just want to take this opportunity to say welcome to a few of you, because I know you're going to be watching for the first time. And then we're going to go straight over to the live telescope views to see that. But anyway, welcome to David, Sushil, Tawny, Deborah, Teresa, Jules, Emmanuel, Terry, Tracy, Thomas, Paul, Martha, Julie, Terry, another Terry, Joseph, Sam, April, Chris, Larry Cox, hello Larry, Jamie, and Nora. And there are so many of you out there tonight who have joined Slooh to watch this close approach of this near-Earth asteroid and learn a little bit more about them. But anyway, let's take a look at our live feed tonight. What are we looking at here? This is our Canary Islands Observatory. It's based at the Institute of Astrophysics in the Canary Islands. If you don't know where that is, about 300 miles off the west coast of Africa. And it's in a perfect place. It's one of the top astronomical sites in the world. Some of the largest telescopes in the world are based here. And we get really crisp skies. We're 8,000 feet up above the Atlantic Ocean, and we get very still air. And what we're looking at here is a special camera that looks 180 degrees width. It looks like it's daytime because the sky is blue and there's something very bright in it. Well, if you don't know what that is, that's actually the moon. It was full moon last night. It was actually a micro harvest moon, which was pretty cool. It's the smallest moon of the year. But let's take a look now, because very low down actually to the south, this asteroid is very low down for Northern Hemisphere viewers. We've got our Chile Observatory, by the way, coming online a little bit later. So let's hop over to our Canary 2 telescope. Now, this is a 17-inch telescope, huge telescope that our members control every night. So we're going to hop over to that, I hope, or one of the other feeds. Studio, bring that up. But anyway, this thing, there it is. Okay, so let's have a look. That is our Canary 2 feed. Now, those are all of the stars because we're tracking in this view the actual asteroid. So what we're going to be looking for in this view, I can't actually see it there, is we're going to be looking at a pinpoint object. And that's going to be the asteroid, because the asteroid is actually moving across the sky quite quickly. So in this particular view, we're going to be tracking at the asteroid's rate. So the asteroid will appear as a pinpoint star or pinpoint object, and then the stars are trailing because it's moving against background stars. But let's go over to our Canary 3 deep sky telescope. Now, in this one, we can see it right in the middle. We can see just in this one, we're not tracking at the asteroid's rate. So all of those other objects that you see in this image stream are stars. And you can just see right in the center, there's one star that looks elongated. Now that's the asteroid traveling. And let's hop over to our Canary 4 telescope, because this is a closer, tighter view. And there it is. We can see immediately, can't we? The stars are sitting there and they're all, reasonably round, getting a little bit windblown tonight. But there, just left of center, we can see our asteroid 2000 QW7. That's the name of this asteroid. In fact, listen, if you're looking, there it goes. Look, it's moving. You can see that in multiple images. We've talked to Dr. Mike Shaw about exactly what we're seeing there, but it's actually moving between long exposures that we take because it's really quite a faint object. But what I was actually going to tell you there is that this thing is moving incredibly quickly. The velocity when it's actually whizzing past Earth at its closest in about 50 minutes time it's traveling at 14,361 miles an hour. Now, that's, I don't know about you, but I can't get to grips with that number. If you want it in kilometers, it's just over 23,000 kilometers per hour. But that is about 3 miles per second. It's 6.5 kilometers per second. That's how fast this thing is moving. And we'll talk to Dr. Mike Shaw about this later. That is also one of the reasons why relatively small objects, this is a large space rock. Don't forget, I told you it's the size of New York's One World Trade Center, 2,000 feet in diameter. It's the velocity. And we'll maybe talk to Dr. Mike Shaw about what that velocity means. It basically means energy. So its mass and that velocity, if it impacted, is wouldn't do us any favors. But anyway, look, it's not going to impact, but what we are going to do is enjoy these live views throughout the evening. Now, if you are watching over at slooh.com, don't forget that you can flick between all of our different feeds tonight, and you can snap your own images and maybe turn them into a time lapse a little bit later, which would be cool. So keep an eye on this. You can see here we've taken now 3 images with our Canary 4 solar system telescope. This telescope is great for planets and small objects and stuff like that. And these images are stacked on top of each other, and we can see then the asteroid moving through. And this is a tiny field of view, so this is great that we're capturing it in this. But anyway, watch at slooh.com. You can also ask us questions in the discussions there as well. We'll have a little look at that later. Check out your questions for me or Dr. Mike Shaw. Now, what have we got coming up then? Well, we have got, I've been talking about him already, but who is he? Well, he's an acclaimed nightscape photographer and author. And Dr. Mike Shaw, he actually runs the Nightscape Club on the Slooh website. So if you're interested in doing your own nightscape photography, then you can listen to his audio shows, join his club, get some great advice from him. But what he does every week, in fact, I'll ask him what he does. So we're going to go to a short break in a minute, and we'll ask him to explain what he does in that club. But anyway, he's going to be telling us, he's going to be doing a back to basics about near-Earth asteroids, what they are, where they come from, what they're made of, stuff like that. He's a materials scientist, actually. And later we're going to be discussing the threat that these rogue space rocks pose to Earth. Now, you might be quite surprised at just how many of these things actually do impact Earth. In fact, we'll tell you about how it started a whole new group of Slooh members who still do track near-Earth asteroids and comets. And that happened back in 2008 when they witnessed one of these objects impact the skies over Sudan, over the Sudanese desert. And they were among the, I think, only 3 people in the world, or 3 groups in the world, who managed to capture images of this object before it impacted the Earth. Anyway, that was the first one. We are also going to be talking about other space rocks that hurtle around the solar system, and one recent discovery that you may have read about, which is everything that we're looking at in these images tonight are they're stars, but planets, asteroids, comets, they're normally from our solar system. But we're going to be talking about a fascinating recent discovery discovered only a few weeks ago, which is an interstellar object. It's come from between the stars, so distant. And it's an absolutely remarkable discovery if it turns out that that's what it's going to be. But anyway, don't forget, you can join the conversation and ask us questions. So go over to the show page on slooh.com and you can join the discussion over there. We are going to take a really short break. And then after the break, I'm going to be joined by Dr. Mike Shaw. Don't go anywhere. We'll be right back.
Slooh is your interface to space. Online telescopes situated on mountaintops around the world await your command to schedule missions so you can capture images of the 1,000 most intriguing celestial objects in the universe. From just $20 per year.
Hello and welcome back to Slooh. We are watching tonight. There it is. That little dash in the middle there. We'll maybe hop over. Actually, let's go back over the Canary 4 view, because that was really cool. We are watching Potentially Hazardous Asteroid 2000 QW7. What an imaginative name that is. In fact, there's a challenge for all of our viewers tonight. If you're watching over at slooh.com or on Twitter, then maybe suggest some names for this thing. But anyway, listen, I am delighted to welcome our special guest tonight, Dr. Mike Shaw. And Mike, welcome to the show. What do you think of these images? It's always quite encouraging and
Oh,
quite
it's
a relief actually
fantastic.
when we see
Yeah.
them.
Yeah, Paul, no, it's a pleasure to be here. Thank you for the invitation to join Slooh's show this evening. And I'm torn between looking into the camera and watching these beautiful images on the screen because it's just remarkable to think about the amount of expertise that it takes to capture these images of this object it's so far away, moving, as you say, so incredibly quickly, and
Yeah.
yet with so many implications about um, so many parts of astronomy and life on Earth and all the things we'll be talking about this evening. But anyway, thank you again. It's a real pleasure to be here.
Well, Mike, I gave you a very brief introduction there, but I did mention that you run the Nightscape Club on Slooh. Uh, Tell us very briefly, before we start talking about the near-Earth asteroids, tell us very briefly what you cover. And you do this on a Tuesday, don't you?
I do. So everyone who's listening, thanks, Paul, for the opportunity to describe the show. It's a really great discussion about really the nuts and bolts of creating your very own nightscape images. And you might ask, what is a nightscape image? And it's really any image that combines a really cool image of the night sky. This could be the Milky Way, it could be stars, star trails, a panorama, it could be a meteor shower, which relates to tonight's show. So a really cool image of the night sky with a really cool image of the foreground. So this could be, a city skyline, if there's not too many lights, a lake, a mountain. You've seen these images all over the place. They've really burst into popularity in the last decade or so. And what our Nightscapes Club and our Nightscapes show does is to tell you how to create your own images with your camera and tripod and all the
Great.
techniques. So everyone get out your pen and mark down Tuesday evenings, 9 p.m. Eastern Time in the U.S., 6 p.m. Pacific Time in the U.S. That show starts around 0100 UTC, and we have a great club in Slooh and a great discussion every week. So looking forward
Yeah, it
to
is.
helping out.
Yeah, and you've already inspired a whole bunch of Slooh members to, even some of them have gone out and bought cheap DSLR cameras to give this a go themselves. But listen, Mike, we're watching now this potentially hazardous asteroid, 2000 QW7. It's going to be closest to Earth in about 40 minutes time. I've mentioned this thing is between 290, 650 meters, about 2,000 feet in diameter. It's moving incredibly quickly. All we're seeing on the screen is this small white dot. And in fact, let's take a look, because I have just been told that we've got our Canary 2 wide field shot working now. And this one is the one that's tracking the asteroid. We're seeing this asteroid. We know it's 3.5 million miles away as a small white dot, Mike. But what is it? What is a near-Earth asteroid?
That's a great question. And for those of you who are just sort of tuning in and just learning about asteroids, they're more common than you might think. And in fact, there's a really rich history of asteroids and asteroid discovery in the history of astronomy. But to the point that Paul just asked, really, if you just go to the beach and pick up a handful of sand, the sand that you're picking up is really a combination of the elements silicon and oxygen and perhaps some aluminum. They're all oxides of silicon and oxides of aluminum. And asteroids really aren't very different than that. There's a different variety of asteroids that we'll be describing, but they all have something in common, which is they're all made out of the same basic ingredients that we have on Earth. And these are the elements that you find in the periodic table. And one of the things that's so fascinating to me about this subject and about astronomy and science in general is that if you look into the universe, everything that you see, everything on Earth certainly, and everything in our solar system, the asteroids, and everything that we'll see to the furthest distance of the universe are all made from the same 110 basic elements of the periodic table. And when you think about it, it's really quite remarkable that those 110 or so elements make up all these different things that we see. But the asteroids are typically basically like a type of rock that you would find in nature on a hiking trail, or as I say, sand on the beach. Some of the different parts of the asteroids, right, have different sub layers of composition, but they're basically just pieces of rock.
So where do they come from? I mean, I think I've heard them described as the kind of leftover rubble of the formation of our solar system. Is that a good description of these kind of space rocks that are floating around the solar system?
That's a very good question. It's almost is it left over or is it really the primordial building blocks that we're seeing? And one of the really cool things about the history of asteroid discovery and what they're how where the what are they is that there's a neat story of patterns in nature. And this is one of the things I think everyone listening might be interested in is one of the things science is really strengths is looking for these patterns in nature and taking advantage of them. So with the periodic table, Mendeleev discovered that there were these relationships between the elements and deduced that there must be these other elements in between and started a quest for the elemental discovery. And it was the same thing with asteroids. Back when this is in around the 1650s or so, the early astronomers were noticing there was a certain pattern to where the planets were in the solar system at the one gap, and that gap was where the asteroid belt turned out to be. And to make a long story short, it was a fascinating story. But the thing about our particular solar system is we have this massive planet Jupiter and Mars, and the asteroids really lie as a belt in between Jupiter and Mars, the asteroid belt. And what happens essentially is that the little pieces of material, these little rocks that are floating out in space, planetesimals, that ultimately formed Jupiter, Saturn, Earth, all the other planets in our solar system, they were just too close to Jupiter, and there were just kind of not enough density there to really come together into a planet, such that every time these little planetesimals would try to get their act together and form a little planet, they just were ripped apart by the incredible forces of gravity from Jupiter, and that's why they just remain left over from the early days of the solar system and why they're so interesting for us to study from an astronomical point of view, because they are these original fragments from the solar system formation that we can study, 4.5, 4.6 billion years ago, that we can study today and learn about our origins as well as the origins of so many other parts of the solar system. So it's really fascinating.
They really are primordial. Now, let's take a look. This is Canary 2. Now, this one here, Mike, is we can
Yes.
see the stars are trailing, but we can
Yes.
see one dot on this
Nice.
image, which is not trailing. And that's because we're moving the telescope at the asteroid's rate. And
Well
we
done.
said
That's
this
very
is,
nicely done.
it is,
Yeah.
that's beautiful. So please, everybody, snap images from this stream, because this will turn into a lovely time lapse a little bit later. But so, Mike, you were talking about the asteroid belt, but and you were saying that's between Mars and Jupiter, but this object isn't. It's a lot closer than that. And last week, we saw a couple of smaller asteroids actually come between the Earth and the Moon. It came so close. In fact, it it wasn't discovered until after it had made its path. So they're not all in the asteroid belt. Some of these asteroids are perturbed and flung into our neighborhood, and that's when things get a bit scary, isn't it?
Well, that's just exactly it. And, the universe, fortunately, is, for better or for worse, a bit of a lottery. And, for if you go back to the history of Earth, I think we'll be talking about the dino killer, 65
Mm.
million years ago. But one of the reasons that we're here having this conversation tonight is that we're living in a time or an era when most of the collisions between asteroids and planetesimals and other objects within the solar system have occurred. And we're at a stage now where things have calmed down quite significantly so that all of these events that have taken place look at the moon. Look at the surface of the moon as one example. The
Yeah.
lack of seismic activity and the lack of an atmosphere combined to preserve these impact craters on the moon. They have craters upon craters upon craters. And of course, the
Mm.
same thing happened in Earth. It's just the plate tectonics and atmospheric erosion to kind of smooth things out for us. But absolutely, you do have these random events where an object will be flung through it's a random combination of events, perhaps, or maybe not so random, and come our way. And as you say, these objects, the one we'll be seeing now in maybe a half an hour or so, is a as you say, a stone's throw away from Earth, and you know, certainly a very productive branch of science, I would think, to continue to study ways to divert these objects as they get closer to us. And hopefully, as you say, you can see them in time, but sometimes you just don't.
Well, we were invited to NASA a number of years ago to participate in their asteroid program. And we met some of the delegates there who were there to talk about mitigation and how we could deflect or destroy, or, think Deep Impact, think Armageddon, all of these
Right.
movies. And what was fascinating to me was, for all of the talk of solar sails or painting the surface so the sun's energy, bounces off it and starts to move this thing. None of these things were practical except the proposals from one group, and it was the Japanese contingent there. And it's, yeah, it was quite odd actually that it was the Japanese contingent who was suggesting this. But the only practical method we actually have is very, very close to what we see in those movies. It is getting somehow a nuclear device up close to one of these things, and frankly, either blow it into smaller pieces, exactly like Deep Impact,
Hmm.
or to manage to deflect it. All of these other
Hmm.
things were technologies which were to be developed, kind of
Hmm.
TBC. But
Yeah.
these exist now. But I mean, frankly, um, if one, I mean, and we are talking about, we've over the years at Slooh, we've tracked some of these. This is quite distant for us, but we're covering it because it's such a large object, and it is reasonably close. But we've been covering some of these near-Earth asteroids that have been closer to Earth when they've whizzed by at the same kind of speed, not quite as large, but within the orbit of our satellites, our
Yeah. It's
artificial
just
satellites. I mean,
incredible to
it's
think about, isn't it? Yeah.
exactly. And we've also seen the very first asteroid discovered in 2014. It happened on New Year's Day. Did we know about it? Nobody discovered it, probably because everybody was asleep on New Year's Eve.
Right.
But
Yeah.
what happened is we found out about it the following day because all of the sensors around the world from the global superpowers, which are there to monitor any nuclear explosions, picked up that this object had hit the atmosphere somewhere over
Really?
the Atlantic. And that was the
Oh,
very first asteroid to be discovered in 2014. We didn't even see it coming. And
wow.
we've
Incredible.
we've we've covered loads of these things, including some fairly big ones, which have made their close approaches to Earth only days after their initial discovery. So this is what this NASA program was, and we're going to
Wow.
talk a little bit later, Mike, about how all of that got a group of Slooh members together to actually start their own monitoring and tracking program. And to date, they do this kind of stuff every single night, and they help determine the orbits of these things. So we know where they are, we know how close they're going to be, and we can tell a little bit of how big they are as well. On that score, Mike, before we just to round out this segment, uh, I gave this huge size estimate, 290 to 650 meters. How do we come to that estimate, and why can't we tell how big this thing is? I mean, it's big. We can see it here in our live image streams. How do we determine how big an asteroid is, and why is there such a huge range that we've got?
That again, that's a great question. You covered a lot of ground there. I mean, this is really such an impressive feat to think about diverting these objects. But yeah, when we look at these images, I thought it would be worth just for those of you who are maybe not as familiar with tracking moving objects like these against other moving objects. One of the fundamental problems with tracking anything in the night sky is the fact that the Earth is rotating, so that everything appears to be moving. So if you simply, and this affects us in our nightscape community very much so, that we plant our cameras on a tripod, and we have to limit the shutter speed before we can actually see the stars moving. And what's so phenomenal about the view that we're seeing here through, I believe it's with the current view, I'm having a hard, is it Canary 3 right now, is it?
No, it's Canary 2, so this is our
Canary
17-inch
2, okay.
telescope. Yeah.
Yeah, so that's okay. What's remarkable about this is that it's like if you've ever seen those photographs, let's say, of a person on a bicycle moving against a blurry background. So the person on the bicycle is nice and sharply defined, but the background is blurred to really give you a sense of speed. And that was the image that we just had. We had a pinpoint asteroid, which is the person on the bicycle, moving against these background stars, which are streaking because they're blurred out. And this has to do with how we kind of go to Paul's question is how do we measure how big these things are? As we look at astronomy is an observational science, so we can't stick out a yardstick, we can't, bounce a radar signal off of it or anything like that. So we're just stuck with what we can see. And what we can see really goes through a range of spectral components. If we look at the electromagnetic spectrum, there's a visible spectrum that gives off some light that we can detect with our eyes. There's an infrared spectrum that can give off a certain infrared signature. But what we do is we actually measure the intensity of the light that's emitted from the objects, and if we have a sense with how fast it's moving and how far away it is based on the observations that we can make from the images, we can put all of that together and sort of back out an estimate for the size of the object. But again, it has some error to it because we don't know for sure what the surface properties, let's say, for example, of the object are, or it might not be a basketball, it might be a football, or it might be a stick. So, I mean, when we make an estimate to the sizes, if we have a stick-shaped object, I mean, how would you characterize that? Some sort of an average diameter or something. So that's some of the uncertainties. That these are natural objects, such as like a rock that you would pick up on a hiking trail, or a large grain of sand, and it's certainly not a regular object with a nicely defined thing. And that comes into some of the estimates of the damage that these things can cause too, as we'll talk about in a minute. We talk about the kinetic energy and stuff, but that's a brief synopsis of how we would go about something like that. It's just looking at the light to get from it.
Exactly, and it's why astronomers get so excited when we get these very close passes. This one won't be, but some of the closer passes, they fall then within the range of the radio telescopes, and with the radio telescopes, we can actually define their shape when they're close enough, and build up a kind of 3D model of these things. And that's the only time, though that's really important, because we can then start comparing our models of the brightness, the albedo and size, to what we actually find with these things. I mean, a lot of these things, their surface brightness is darker than coal. These are dark, black, cold objects. But anyway, Mike, we're going to take a short break now while viewers carry on enjoying watching Potentially Hazardous Asteroid 2000 QW7 whizzing by. How long have we got? We've got about 25 minutes before it makes its closest approach. So keep watching all of the live streams. Don't forget, if you're watching at slooh.com, you can be flicking between all of the live telescope views and pressing the Star Share camera button and snapping your own images. Now, what are we going to be talking about when we come back? Well, Mike and I are going to be discussing the threat posed to Earth from near-Earth asteroids. We've already talked about poor old dinosaurs who didn't have a space program, and we do have a space program, but frankly, if one of these things was hurtling towards us now, there is frankly nothing we or Bruce Willis could do about it. Then a little bit later, we're going to be talking about comets and a recently discovered intriguing object that's heading towards the inner solar system, that's our neighborhood, from interstellar space. Interstellar is between the stars, outside of our solar system. How exciting is that? And by the way, any conspiracy theorists out there, the object that we're going to be talking about is not Nibiru. All right, so it's not Nibiru, just so that you're clear. We will also be talking about the group of Slooh astronomers who track and monitor near-Earth asteroids and comets every single night. And don't forget, you can join them. In fact, you can even take part in the training course to learn how to do it. We also, of course, look at absolutely stunning, beautiful objects like the Orion Nebula and all manner of galaxies and nebulae and star clusters and stuff like that through the telescopes that Slooh members control every night. And of course, we are going to be marking the moment closest approach of potentially hazardous asteroid 2000 QW7 at 53 minutes past the hour. Please, I'm going to go and check the discussion on the show page to see if any of you have come up with a snazzier name than 2000 QW7. There's actually 6 numbers off the beginning of its name that I'm not even bothering with tonight. But anyway, don't go anywhere. We're going to be right back after this short break. Bye for now.
Slooh is your interface to space. Online telescopes situated on mountaintops around the world await your command to schedule missions so you can capture images of the 1,000 most intriguing celestial objects in the universe. From just $20 per year.
Hello and welcome back. I'm Paul Cox, and him down there, that's Dr. Mike Shaw, guest tonight, expert guest tonight, and we are talking about the potentially hazardous asteroid 2000 QW7. This thing is larger than New York's One World Trade Center tower and twice the size of London's Shard Tower. It is traveling at a staggering velocity of 14,361 miles an hour. And we're going to talk about exactly what we're looking at in our live streams in a second. But we've got a question, Mike, from Raymer, Slooh member Raymer M. And I think it's he, but if not, excuse me, he or she has said, has this asteroid's orbit been calculated yet? And if so, what is the time it takes for one orbit? Do we know that?
That is a very, very good question because it really relates to the the interstellar object that we're going to be talking about in a moment. And the quick answer is I don't know if the orbit's been calculated, Paul. So I don't know if that's
Well, that
your
bit that bit's an absolute certainty,
yes.
because it's that it's that orbit, and that calculated orbit that we're able to pinpoint it now, in the
Okay.
telescopes. But
Oh, well, there you go. Okay.
I'm not aware, actually. We will take a look, actually. I'm not aware of its orbital period. In other words, how long it takes to come around the
No,
sun.
I'm
I mean, it was
yes.
discovered in 2000, so we know that it was probably fairly close then. But we will get back to you on that one a little bit later. But let's talk
Yeah.
about our live image streams here, Mike. So this is our Canary 4 telescope. It's called the Canary 4 solar system telescope, and it's because it's got quite a small field of view and is tuned really nicely for planets and small objects. And can you explain to viewers what it is we're seeing here in this image stream?
So this is a great question, and I thought it would be useful just to review the term field of view, the what's a wide field and narrow field and this sort of thing. And the the when we talk about the different telescopes that Paul's going to go through shortly, one of the biggest differences between them, other than their sheer size and complexity, is how much they how much area they view on a given when you look through the telescope, what's the area that you see? And so that term is a little deceptive because when you think about zooming in or zooming out with a telephoto lens or not, it's really the angle that is subtended from one side of the image to the other. So in other words, if I hold my, let's see what this looks like. If I hold out my hands like this, it's like this would be a wide angle, this would be a narrow angle because it's a very narrow angle. And in this case, the Canary 4 is a fairly narrow angle because it allows us to really zoom in on the planets and the moon, for example, and the planetary nebula. In this case, so here's what we're looking at here is we've got a whole bunch of stars in this field of view. And then right in the middle, the view that I see has three dashes. And those three dashes are the asteroid that we're looking at. And it's actually moving with respect to the stars. So it's as if we are looking at a racer on a track, a sprinter that's on a track, and the sprinter is sprinting along, and we can only just get a few snapshots of the motion of the sprinter as it moves. And so it's this motion that we can then use with an estimate of its distance to calculate its speed with the different degree of uncertainty that Paul was mentioning. So it's a phenomenal thing that we can just pinpoint out this particular field or spot in the sky and resolve this tiny object moving with such high velocity so easily.
So let's bring up a couple of the other views. Let's take a look at our Canary 2. Now, this is one of the largest telescopes that Slooh's got. We're not using the very big one tonight, which is a half-meter telescope. And when we're talking about the size of these telescopes, when I say 17 inches, which is what it's about 400 millimeters, something like that, we're talking about its primary mirror, the largest piece of glass in the telescope. So, Mike, here we've got a far larger field of view. Now, what we haven't said actually, and we must give a shout out to Andrew Dumbleton, who's our ops manager. He's actually controlling this telescope manually tonight. Now, normally this is controlled in exactly the same way by Slooh members over the internet on Slooh's website. But this asteroid is very, very low down, close to the southern horizon for Northern Hemisphere viewers. Now, we were hoping to bring online the Chile Observatory, but that just got clouded out right at the last minute. It's far better placed from the Southern Hemisphere. But the reason why Andrew's having to control this telescope manually is because it's so far south that normal operations can't do it. So he's had to point it lower than we would normally allow it to go. We did some testing last night and we were a bit nervous because there was a possibility that we might actually crunch the telescope into some other equipment.
I can imagine.
So here, Mike, this is an incredibly sensitive telescope. It's got a CCD camera on the back. These are not the cameras that you use for your nightscape photography. You know, these are ultra cooled scientific CCD cameras. This one actually at the moment is operating at minus 40 degrees centigrade. So maybe you can tell viewers, why on earth do we have to cool a camera down, you know, to take a shot like this?
Excellent, excellent question. Boy, there's so much good stuff to talk about here. So
There is too
the
much.
no, I mean, this is like I always. It's one of the things about my weekly shows. I always run out of time. I think a million things. So the quick answer to your question is that the electronic device. So what is a camera? What is a sensor? So your eye has a retina. The thing that you're viewing your screen to see us talk is your eye. That's the retina in your eye. And cameras have the equivalent retina. It's called a sensor. It's made out of a semiconductor device. And for your cell phone, your smart device, your pad, your camera, your DSLR or mirrorless camera, those devices are typically made out of silicon. At least I believe that's the latest incarnation of these things. And silicon is a device that silicon-based devices can operate quite successfully over a range of normal temperatures. Now, when we start talking about the highly sophisticated cameras that Paul was mentioning used in astronomical imaging, the basic functionality of those devices and the amount of thermal thermally induced or temperature induced, I'll just call it noise or pixelation, or I'll just call it noise for lack of a better term, because that's what we call
Noise,
it,
yeah.
is get just becomes much better when the temperature is lower. And so the way this is accomplished is through usually they're called thermoelectric coolers, or a little other solid state device that's attached to the sensor, and they're operated by electricity. And they're like little miniature refrigerators. They're really fascinating, and they just actually extract heat away from the sensor to cool them down to the necessary temperature for them to function properly. So that whole thing is just a fascinating subject of discussion. But I'll try to stop talking now.
It is. Actually, we will come on to that in my own audio shows every week, where I do talk a little bit more about the equipment. But what we're seeing in this image then is Andrew Dumbleton, our ops manager. He's actually controlling this. He lives in the UK, in Warwickshire, and he's controlling this telescope, just like Slooh members do around the world every night, but he's doing it a slightly
That's
different way.
incredible.
And what we're seeing here is all of the brightest, slightly elongated white lines. Those are the stars, and the dot just above, center of the image. It's the purest dot in this entire image stream. That is our asteroid. That is our target, potentially hazardous asteroid 2000 QW7. Now, I did take the opportunity. I was listening to you, Mike, but I did take the opportunity. This does orbit only once every 19 years. So this is only the second time that we've seen it, because its name, we haven't really discussed its name, but you know, for this particular one, 2000 is its year of discovery. The QW and the 7 mean which month of the year, which week of that month, and then which number it was discovered in that particular moment. But we were going to talk, Mike. Actually, we got a. You know, we're both as bad as each other. We're like dogs with a squirrel, and we get, you know, misdirected by these fascinating images. But we were actually going to be talking about the threat from near-Earth asteroids. Now,
Yes.
we're not going to go into too much depth about this, but you know, we have experienced a couple of these. There's one that we know about, which was it was the Chicxulub crater. Is that right? Is that the dino killer? So tell us a little bit about that one.
Well, this is an interesting story, because this is really it's probably one of the scariest discoveries I think I've heard about in my history of science knowledge. And this is the event that wiped out. This was at the end of the Cretaceous period, about 65 million years ago. And again, a fascinating story of discovery in science. Is like, how do we know this happened? And for a long time, there was a lot of theory about what wiped out the dinosaurs. Was it a volcano? Was it a plague of locusts? What actually was it? And curiously, there was a team of geologists that discovered they were doing their geological studies as geologists do. And one of the things they discovered during their geological studies is that as they studied the structure and the composition of rocks on Earth that were present at around the end of the Cretaceous period when the dinosaurs were wiped out, they noticed a really unusual thing. And what they noticed was that there was a thin layer of this, I won't say foreign material, but a very unusual layer. A very rich in the element iridium, which is a high atomic number, fairly unusual element to find just as a single layer on these in these rocks. So these geologists were curious about this, and they visited, along with other folks, different places around the world, and they found the same thing. That all over the place there is this thin layer of iridium-rich material at the same time at the end of the Cretaceous period, and the light finally went off in their head that, oh my gosh, what likely happened is a huge meteorite. Their estimate is something like 6 or 7 miles in diameter. Think about that. Smashing into the Earth, and the meteorite itself was the carrier of the iridium, the source of the iridium. And when the meteorite splattered into the Earth, all this stuff just got kicked up and thrown up into the atmosphere, and it just settled out like iridium rain all over the Earth. And of course, a lot of bad things happened after that, but that was the Chicxulub impact of around 60. And it happened in the Yucatan, in part of the peninsula in Mexico. And now you can look at these amazing color images taken from space of it's like 110-mile diameter crater remnant buried underground. It's just a phenomenal thing to just imagine what a horrific, and of course there's nothing you can do about that. That's just the end of it at that point.
And we're still learning a huge amount about that particular crater. It was only a couple of years ago that they were doing some more boreholes down into it to understand the distribution and the size of this impact, because an object actually, you mentioned the moon earlier, and we look up at the moon, and if viewers go out this evening, have a look at the micro moon. It was full moon last night, but it's kind of still full moon tonight. But it's a micro moon. The moon's orbit is elliptical, and it just happens to be at its furthest away from us. So it's actually 30% dimmer than the largest full moon of the year. But anyway, I digress on that one. But you mentioned the impact craters that are still there, and they range from huge, enormous things, miles and miles wide, to really small things. And we saw them even with the Apollo astronauts. Yes, they did land there, conspiracy theorists. Even micrometeorites we saw, kind of tiny little craters. They were able to get through to the moon's surface because, as you said earlier, there's no atmosphere. But obviously we enjoy an atmosphere. So actually an object has to be quite big to be able to impact Earth's surface. But even when they explode in the air, Mike, they can still cause quite a lot of damage. And we've seen 2 examples of that within 120 years-ish. We had Tunguska, where we got photographic evidence, and we've got Chelyabinsk. What can you tell us briefly about those 2 impacts, which I believe were classed as airbursts? Is that right?
Yeah, certainly. Yes, the Super Bowl. There's all these great. This is going to become a
great names,
show if
aren't
we're
they?
not careful. Just before I forget, though, I just want to make the point, looking at these images, that I think it's important, if you're new to this, if you're just joining, to recognize and appreciate the fact that the telescope is moving while the image is being made. And that's why the stars are being elongated. So I just want to say explicitly that we're literally, the Slooh team has this telescope tracking the asteroid as it's moving against the sky, and that's why the stars are streaked out, because they're not moving relative to the asteroid. So the 2 the Chelyabinsk and the Tunguska events are essentially what's happening is for something to reach the surface of the Earth, it has to be a meteorite. For a meteor to become a meteorite, it has to be I've got so many things I wanted to add to that. about the size of about a centimeter or so, about half an inch or so in size, in order to make it to the size of a marble to reach the surface of the Earth. But what happens is, when you think about it, you have this piece of rock, an asteroid, let's say, or a meteoroid that's coming into the Earth's atmosphere. And of course, we understand that there's a lot of friction that takes place, heating up the meteor, and whether or not it becomes a meteorite depends on how much stuff there is to begin with. But what happens is, for these events that we're the Chelyabinsk one, which is a super bolide, which is a large
Hey,
incandescent.
Mike.
Oh,
Sorry, I'm
are we
going to
coming up on the?
interrupt you.
Oh,
We
yes,
are
please.
at closest approach right now.
Woo!
So let's take a look at this fabulous live image stream coming in from our Canary Islands Observatory. Mike's explained most of the slightly elongated white objects in the image stream. Those are stars, but the white dot, now it might not look that impressive to you if you're new to astronomy, but that white dot just above center, totally crisp, that thing is the size of New York's One World Trade Center, twice the
It's
size
incredible to
of
think about.
London's Shard Tower. It is traveling at a velocity of 14,361 miles per hour. That's 6.42 kilometers per second. This thing, first of all, is massive. Secondly, it's going very fast, which means it has a huge amount of energy. And right at this moment, it's 3.5 million miles
There it
away.
is.
And that does sound like a lot, I grant you, but I say it every single time we watch these things. Those numbers are tiny. It is a stone's throw in astronomical terms, especially when we talk about our solar system. And this is a pretty big stone to throw, isn't it, Mike?
Well, it is.
There
I
we
mean,
go.
it's just incredible. I mean, to think about it, and you can now say, and with some degree of relief, that it looks like it missed us, because if this is its closest approach, it's now receding from us, so we can all sleep a little bit more easily tonight.
So the
Uh,
calculations were correct. Good.
the
Okay.
calculations were in fact correct. Yes, it's just an incredible thing when you really. I mean, yeah, it's just to be able to see that object, here's something else just to make very clear: is the stars that we're seeing here themselves are emitting light because they're stars and they give off light. That's what stars do. But the asteroid is not a source of light; it's reflecting light from the sun. And so the light that we see here from the asteroid is very different light than we see from the stars, because the light from the asteroid the asteroid is acting like a little bit of a mirror for the sun. So this light from the sun has to go all the way out to the asteroid, hit the asteroid, and then it has to come all the way back. So when you think about just the tiny fraction of sunlight that managed to make it back to Earth from the asteroid, it's really quite a staggering thing to think about. So I just wanted to make that point as well. I kind of can't remember what we were talking about when we got to
Well,
that point of.
I think we'll move on anyway, Mike, because we've
Sure. Okay.
overrun a little bit, and I do want to get to some
Okay.
questions that we've got from people.
Yes. Yes. Please.
And we're not going to go to another break. We're going to carry on now while we're watching. Thank you
Sure.
very much, Andrew Dumbleton, Ops Manager, controlling the
Fantastic.
telescope at the moment. And don't forget, these are the same telescopes on top of this high volcano in the Canary Islands, 8,000 feet altitude, um, up there with loads of professional telescopes, some of the largest in the world, that all Slooh members control every single night. And don't forget, a lot of the stuff that people view through the telescopes are in color. If you haven't yet
Yes.
seen the Orion
Oh,
Nebula or the
it's incredible.
Dumbbell Nebula or the planets or a lot of these other objects that we look at through the Slooh telescopes every night, it is going to knock your socks off. But Mike, we've got a couple of questions here. And one of them is from David, and he's asking, are we going to be able to see this in the night sky without a telescope?
No.
No. And because it is so faint. I mean,
No.
you're used to
Yeah.
this in your nightscape photography.
Yeah.
We talk about magnitudes, which are how we classify stars and other objects in the night sky. It's normally thought that if you've got superb eyesight, if you forgive me, Mike, but slightly younger than both of us, got nice,
Quite
fresh,
all right.
young eyes, under ideal conditions, you could see down to about magnitude 5 or 6. With a pair of binoculars, you might get down to 9 or 10. Personally, I think that those are always slight exaggerations. But
Mm,
this tonight is magnitude 14. So
right.
you need a telescope to see it. And in fact, one of our long-time members did answer this in the discussions, and Stephen Aman has actually said you need an 8-inch telescope to see down to this kind of magnitude. But of course, don't
Right.
forget that we've got these large telescopes high above a lot of the atmosphere, but also we're not looking at them through an eyepiece, which
Right.
reduces a lot of the light. We've got these ultra sensitive cameras on the back of it, taking long exposures and then combining all of those exposures up so that we
Yes.
can see these incredibly faint
Yes.
objects in this kind of clarity. So that's a pretty good question. But uh,
Yes,
we
it
were
is.
going to we were going to talk, Mike, very briefly about how you monitor near Earth asteroids. Now, there's a science called a field of astronomy called astrometry. So, what's astrometry about?
Well, that's a good question, Paul. I mean, it's not something that I'm super familiar with, but I think what I would say to that is that there is a network of, I mean, there's so many of these objects out there. There's something like over, I think, 500,000 objects that are floating around. And when you think about what are the objects that are out there, in addition to asteroids, these near-Earth objects, now there's a bunch of space debris left behind from all the different space missions that we've had. There's comets that we know about that can come within a near-Earth um, environment, and really it has to do with the near Earth object category in at all. I don't think we define that through the show, but it's really something within a specific distance to the Earth, and it's about 1.3 astronomical units, which has to do with the distance from with 1 astronomical unit is the distance from the Earth and the Sun. Um, but it really, in order to, my point being that in order to really monitor all these NEAs and the potentially hazardous asteroids, it has to be done, as you mentioned, automatically, Paul, with the object that happened on the New Year's Day on 2013. So
Mm.
I guess I would just say to my limited knowledge of that term has to do with the sort of remote routine monitoring of the objects in the night sky. But perhaps you have some more to add to that.
Well, yeah. So astrometry is, and it's always you have to take more than one set of images of an object because you need at least or three to then build up to ascertain
Yes.
its speed and its
Mm-hmm.
direction. But
Mm-hmm.
if any viewers out there, if you've stuck with us this long, thank you very much. We're only going to be another 5 minutes, I promise you. But if you've stuck with us this long, you'll probably be interested to know that there is a group of Slooh members who monitor and track near-Earth asteroids and comets every single night. Probably one of the most active groups in Slooh, other than our astro imagers. So you've got a group of people who are really doing what we call art astronomy, which are the beautiful images you see in the magazines and stuff like that, as well as obviously Mike's nightscape photography as well that we see. But then there's the science side of things as well, and they track these asteroids. And one of the reasons why they do that is because a lot of these asteroids now are discovered by these automated surveys, like Mike said. And these automated surveys cover virtually the whole sky every night. So they mop up all of the discoveries. But what they don't do is they then don't carry on and monitor those asteroids. So many of them get lost. There was one that we tried to capture a number of years ago, and we dubbed it Moby Dick because it was lost. So you've got these multi-million-dollar surveys, professional surveys set up to actually discover these things, but then nobody does the follow-up observations so that we can keep track of them. And that's what this group of Slooh members does. And Mike, you probably haven't heard this story, but we will just finish off with it. I think we'll have to tackle our lovely interstellar object in our
Okay,
audio cast, where
I
maybe we
think
can
so.
capture, because I know Slooh members have already started trying to capture this interstellar comet. We will
Yep.
just maybe sign off, just maybe 60 seconds at the end, Mike. But how Slooh members got involved with this? Slooh's been around since 2003. And it was the night of October 6th, 2008. And I remember it so well. And one of our members, Tavi Greener, heard about an asteroid that had only been discovered earlier on in that day, just a few hours before. And astonishingly, astronomers captured enough data to calculate it that it was going to impact Earth that night. Now, what
What?
Tavi was able to
Wait a
do
minute.
was exactly, and this was the first asteroid which had ever been discovered before impacting Earth. So what Tavi did is she immediately scheduled the telescope. She got together with a couple of other members using these telescopes that we're using tonight, and
Really, I
she
haven't heard this
scheduled the
story.
telescope for where this asteroid should be. And don't forget, early on in their discoveries, the orbits are not that well known. This thing had only been discovered a few hours before, 11 hours before, something like that. And it was named 2008 TC3. And they watched in amazement. Don't forget that Slooh is all about live telescope views. So all of our members were watching these live images coming in of this
Wow,
asteroid. They were one of only a handful of people who managed to capture images of this space rock before it impacted in the
that's
Nubian
incredible.
desert in Sudan. And it was absolutely incredible, and it caught a lot of our imaginations. How on earth can we be in the 21st century and be so open to having one of these things impact us
Yeah,
and not know about it beforehand?
right.
Now, huge amounts of this particular asteroid, I think it was calculated to be 80 tons or something like that, only
Wow.
about 13 feet in diameter, so it wasn't big. But a lot of the fragments did make it down to the ground, and they did collect up. They scooped up, I think hundreds of kilograms worth of material.
Wow,
But
that's a good
that's how
haul.
Slooh got started off. And if you are interested out there in joining that group, then they train you how to do it, how to use the telescopes to track these objects and make submissions. So you make your astrometric measurements of it. In other words, its precise position in relationship to the background stars, and you make a report to the Minor Planet Center. Now, Slooh members, since that time, way back then, have made nearly 10,000 submissions to the Minor
Really?
Planet Center. Yeah, and I
Wow,
mean, that's an extraordinary number. If you look
that
on the
is.
league tables, it's absolutely extraordinary. So, listen, Mike, we will just finish off as we still watch Potentially Hazardous Asteroid 2000 QW7 still whizzing its way. Thankfully, now it is moving away. We're not going to see it again until
Right.
2038 or something like that. But talk very briefly, and just literally a couple of minutes. What is this fabulous discovery only a couple of weeks ago?
Well, great question. So, in a nutshell, everything we've been talking about tonight with the asteroid and the asteroid belt and Earth and the moon is within our solar system. And of course, that's our sun, the 8 planets, Pluto, and so forth. And I'm glad we brought this up, Paul, because I'm dying to talk about hyperbolic orbits since the beginning of the show. But this goes back to the question of how do we know the calculated orbit of this asteroid? And the reason that's such a great question is because the orbit is means that it's a cyclic event, that it goes around and around and around the sun, because the sun is the center of mass. The sun and the asteroid are pulling on each other, and the asteroid's moving, so there's a centripetal force that's keeping the asteroid in its elliptical orbit. Now, if you think about, if you go all the way back to your days of mathematics, excuse me, if you haven't had those days of mathematics, now's your chance to have a taste. But if you think about a cone, just like just an absolute cone, like an ice cream cone or a
Yep.
rocket cone or anything else that's a cone. You think of two cones, or just think of a single cone. And if you slice the cone horizontally, you have a circle. So that's a conic section. If you slice the cone at an angle, then you have an ellipse, which is an elliptical orbit. That would be an orbit of the asteroid. But if you slice the cone vertically, which is just parallel to the tip of the cone, then you have it's called a hyperbola. Excuse me. The curious thing about a hyperbola is that it never meets. It's a U-shaped curve that just never connects again on the far side. And what's curious about this comet, I'm trying to remember the name of it, Borisov, yeah,
Borisov, yes.
is that it appears to be on a hyperbolic orbit, which means that it isn't coming around the sun. It's coming in from beyond the solar system, passing through the solar system, and then exiting the solar system. And this is from, as Paul was mentioning, from interstellar space. So this is interstellar, meaning not our solar system. And what is absolutely incredible to me about this is that, like the first one, Oumuamua, I think it was just a couple of years ago, this is only the second time that this has ever been discovered. And I think to me it brings us one step closer to discovering other forms of life, because this is one of the theories as to how life got kick-started here on Earth is from a meteorite, from an asteroid, or from a comet, and maybe it's from a different from interstellar space that has the trace organic molecules that kickstart life as we know it. So there's just so many things that are exciting about this discovery, and I'd urge everybody to stay tuned at Slooh and the rest of the news media to follow this exciting discovery, because this really is something in your lifetime that we're watching unfold.
And Slooh members are already capturing images of it. Now, we've got 1 minute before the show stops. We've got one last little thing, question from Rick A. Hi, Rick. Rick's actually one of our latest graduates for the A-Team asteroid monitoring program, and he did a brilliant blog, and we will make that available so that people can read Rick's blog that he did during his training. But anyway, we have now literally run out of time. So before we close down and get cut off, Mike, thank you very much indeed. Thanks to everybody in the studio. We hope you've enjoyed watching these live image streams of Potentially Hazardous Asteroid 2000 QW7. Keep an eye open Tuesday for Dr. Mike Shaw's Nightscape audio show, and I'll be on next week with a special solar cast as well. But that is all for us tonight. Thank you very much for joining us, Mike.
Thank you, Paul. It was a pleasure.
Good night, everybody.
Good night.